All right, this is Physics 1101, Fall 2022, Exam 4 review on chapters 10 and 11, which are fluids, include fluids, and discuss simple harmonic motion, oscillation waves. So this will also include Lab 9, which is on Archimedes Principle. Lab 10, which is on the pendulum. Again, and Lab 11, which is Meldis experiment, which is a vibrating string. Okay, so that is the lab. That is what the exam will be on. Be approximately like the other exams. It'll be approximately 16 multiple choice and about 5 to 6 short answer problems. Okay, so, and the exam, okay, check the dates for the exam. It'll be the first week of November, or middle of November. As far as that, I'll have the dates posted as far as exam 4 is concerned, again on chapters 10 and 11. So I'll go through some of the topics here again. So check the lectures for each of these. So fluids, again, chapter 10, fluids. All right, main thing is we're dealing with liquids and gases. All right, we're not dealing anything with solids in this case. So that's the case. So again, just dealing with density, mass over volume, as far as liquids are concerned. Again, some of the densities of liquids and gases. So, and again, we're dealing with either grams per cubic centimeter or kilograms per meter cubed. And the basis is H2O, which has 1,000 kilograms per meter cubed or 1 gram per cc. So that's the basis. That's where the metric system kind of came in as far as volume is concerned, and those cases there. All right. Dealing with pressure, don't forget that. All right, pressure is force over area, which is, newtons per meter squared, which again is a Pascal. And we've gone through the density. Pressure is given by rho GH. So with basis of pressure, we have, again, 1 atmosphere pressure when dealing with liquids. 1 atmosphere is 14.7 pounds per square inch, or 101 times 10 to the 5th pascals. So approximately 100,000 pascals is 1 atmosphere. So the unit of pressure in terms of newtons per meter squared is the Pascal. All right, and then as far as, again, depth, it's only depth that makes any difference, not the breadth of it. So depth is what makes the difference in pressure. Okay. Don't forget on section 10.5, Pascal's Principle. All right. Now we had this container, so force F A times A, area A equals F B times area B. No, oh, never mind, the pressure is the same. It's going to be FA over area A, which is pressure A, which is equal to pressure B, which is FB over area B. So we have this area, this is A, B. The pressure is the same on both sides. So this is a bigger area. So this can lift up a bigger force, but much slower than the other one. All right, so if you press down here, this is what a hydraulic is. All right, FB, the area is spread out, the weight is spread out, so this can actually lift a higher force as far as that's concerned. Okay. We have Archimedes Principle, so that's section 10.5. Archimedes Principle, which is again the basis of lab 9. This is the fact that a object in water is going to feel, this is the weight of gravity, this is the buoyant force, so the net weight it actually would feel, Fn, would be the weight minus Fb, which again allows us to figure out the density of an object from the weight Fw over Fw minus F net. So we can't measure the buoyant force directly. We hang it in air. Again, if you just hang it in air, this is F weight. We hang it in water. That's the net. The difference is the buoyant force. So this actually ends up being Fw over Fb. So the more dense an object is, the less it's going to lose weight in water. And then if it's floating, as we had, right, the fraction that it's above, so this is H2, H1, then the density and this is H, then which is total, where H1 plus H2 equals H. Then the density compared to water, density compared to water will be H2 over H. So again, the less dense it is, the less it's going to be. If it's the same density as water, then it'll be just right there. If it's very light, like a piece of styrofoam, barely any of it will be submerged. All right? So that's part of Archimedes Principle. So keep in mind this equation, because we're trying to, and this will give us the density. then, final part here, we have a continuity equation. So again, we have V1, A1, V2, A2, then V1, A1 times V1 equals A2 times V2. Okay, so if this area is much bigger than this one, V1 then V1 will be much less than V2. So this is how it'll come out much faster here. It's like water coming into a hose. You have a small nozzle, it'll come out very fast. That's what we call it, continuity equation. And then that's that part. Then we finish up with Bernoulli's equation. So here's the expression here, continuity equation. Bernoulli's equation. So if you have an airplane wing, this is P1 pushing upwards, P2 pushing downwards. Then with air, which has a certain density to it, this is V2, this is V1. The pressure, P2, plus 1/2 rho V2 squared equals P2 plus 1/2 rho V1 squared, which means if V2 is going faster than V1 because it's going over a plane wing, it's taking longer, so it has to go faster for them to meet the end, then P2 will be less than P1, and we have lift. So that's Bernoulli's principle. I've done some demonstrations of that but that's the principle of how but that's the principle of how a plane wing lifts. It's got the design such as that. So we're not going to deal with the difference in height. That's irrelevant for the most part. So this is Bernoulli's equation as we are using here only for a conceptual basis. So we're not going to be doing any calculations. If you were, an aeronautical engineer, of course you would need to understand this equation as far as how it works, as with plane flow and such as that. So that's chapter 10. I'm not going to do anything else as far as Torricelli's principle. Baseball works about the same way as far as that's concerned. Talked about that a bit as far as how using a baseball, the curvature with the stitching combined with any scratches on it allow it to curve. Use Bernoulli's principle to make the same effect. So that's chapter 10. All right, for chapter 11, all right, we have oscillation of waves. All right, again, and this will be dealing with the pendulum, which is lab 10, and the Melz's experiment, which is lab 11. So So again, simple harmonic motion, we talked about that. Simple harmonic SHM. As far as that's concerned, it's based on a spring having a force of minus kx, where this is in newtons, this is in meters, and this is in newtons per meter, which is a spring constant. We talked about that as far as based on this effect, that an oscillating spring has simple harmonic motion, which is a sine curve. So if this is amplitude and this is time, then it's going to have about the maximum, this is the amplitude plus minus, as far as that's concerned. So we count the time, right? The distance between these, the peaks, is the period, and the frequency is 1 over the period. So this will be in seconds. Frequency is 1 over the period. All right. So getting into potential energy in a spring, right? All right, so potential, we have a spring. Again, compare this to gravity. We have total energy is 1/2 mv squared, which is kinetic energy plus potential energy mgh. So for an oscillating, for a ball bouncing up and down, this is constant. For a spring, total energy, which is constant, is again 1/2 mv squared plus 1/2 kx squared for an oscillating spring. Okay? As the spring oscillates up and down, the speed and the energy due to extension is constant. Again, the potential energy of a spring is given by 1/2 kx squared, and this is potential energy of gravity. All right. So as we talked about, the oscillating spring oscillates between potential, kinetic, but the total energy stays constant. All right, total for a spring, the period, so we talked about the period of a spring, is 2 pi m over k, which we talked about. So it depends only on the mass and the spring cut. This is k. Mass and the spring cut. Doesn't depend on the oscillation, how fast, how much you oscillate it. It only depends, so the amplitude makes no difference. It's mass over the spring constant, gives us the period. And again, the frequency is 1 over the period. So that's for a spring. While we're at it, for a pendulum, which has, I'll just put this up, and this is the Lab 10 pendulum, hanging mass, length L. You oscillate it back and forth this way, all right, and time the period for it to come back the same point. So the period is when it goes and comes back to the same point, or if you leave it at one end, how long does it take to come back to the same point? So for there, the period is 2 pi. Make sure I have that right? L over G, where L is the length of the pendulum, and G is the force of acceleration of gravity, 2.9 meter, 10 meters per second squared, or 9.8 meters per second squared. Depending on how precise you're trying to do calculations. For generally problems of where you're just trying to solve the concept, this will be fine. Again, it has nothing to do with the mass of the pendulum here hanging. It has nothing to do with the amplitude. That's why Galileo was able to realize back in the late 1500s that a pendulum would make an excellent clock, because as it started to wind down, it was still oscillating at basically the same rate. So that works very well there. If we look at those type of concepts, and again, we look at amplitude, x is a cosine omega t, where omega is 2 pi times the frequency. So this is in, as we have from chapter 5, this is radians per second. So the radians is 2 pi times the frequency. And then finishing up here, on types of waves. Again, the speed of a wave is the wavelength times the frequency, where this is meters, this is meters per second, and this is hertz. And again, for speed of sound, it's approximately 340 meters per second. Or again, later, speed of light, so sound. For light, and we get later on in the second semester, it's 3 times 10 to the 8th meters per second is the speed of light. All right, and then finally we have comparison of we have, again, just comparing transverse versus, on the top, transverse wave versus compression wave. And the transverse wave can only transmit through solids, while a compression wave can transmit through solid, liquid, or gas. And I've talked about that, how the difference of earthquakes, because an earthquake produces both a shear wave and a compression wave, and the shear wave can only go through solid, while the compression wave can go through solid or liquid. So it gives us an idea of what the interior of the earth actually is made of, whether it's solid or liquid in parts, which it actually means is more complicated. It's not a solid block as far as that's concerned. Okay, then, all right, then last thing, so that's last thing, this has to do with Meldus experiment, which is on standing waves. And I'll just, again, amplitude is how high it is. So we have harmonics, lowest harmonic, which is the wave goes up and down. Second harmonic, we have one node in the middle, antinode, and third harmonic, 2 nodes and 3 antinodes. And we can get into the wavelength frequency. So we have first harmonic, second harmonic, third harmonic. So The harmonics are all multiples of the fundamental sound, fundamental vibration, which we see this is part of the Meldus experiment. So that is lab 11. All right. So again, that is for exam 4. Check the days for that. So have a good day.